There is a force operating right now at this exact moment on every atom in your body, on every grain of sand beneath your feet, on every ocean, every mountain, every continent, every moon, every planet, every star in every galaxy across the observable universe. It does not rest. It does not negotiate. It has no off switch. And yet, despite being the weakest of all the fundamental forces of nature, roughly 100 septillion times weaker than electromagnetism, it is the only force that has shaped the large-scale architecture of the entire cosmos. Every structure you have ever seen in an astronomical image, every swirling arm of a spiral galaxy, every towering pillar of gas and dust where stars are born, every dense cluster of thousands of galaxies bound together across hundreds of millions of light years, all of it, every last piece of it, is the direct product of this one force acting patiently, relentlessly, over billions of years. Gravity, not a mysterious energy field. Not a cosmic glue invented by science fiction. A fundamental interaction, described with extraordinary precision by the physics of Isaac Newton in 1687 and then revised with breathtaking depth by Albert Einstein in 1915. And yet, even today, with all the computational power of the 21st century behind us, with space telescopes orbiting hundreds of kilometers above the atmosphere and gravitational wave detectors sensitive enough to measure a distortion in space-time 1/10,000th the diameter of a proton, gravity remains the least understood of all the forces. We can calculate its effects across cosmic distances with extraordinary precision. We cannot fully explain what it fundamentally is. That tension, between what we can measure and what we cannot explain, is the engine of modern astrophysics. Consider the scale of what gravity builds. The Sun, which contains 99.86% of all the mass in the solar system, exerts a gravitational pull strong enough to hold Neptune in orbit at a distance of approximately 4.5 billion kilometers from its center. At that distance, a beam of light traveling at 299,792 kilometers per second takes roughly 4 hours and 10 minutes to make the journey one way. And yet the Sun's gravitational field reaches that far, holds Neptune locked into a near-circular orbit, and keeps it moving at an average speed of approximately 5.4 kilometers per second year after year, century after century, without any physical connection whatsoever. No cable, no rope, no medium carrying a signal, pure geometry, according to Einstein. A curvature in the fabric of space-time produced by the mass of the Sun, so deep and persistent that Neptune has no choice but to follow the curve. Now scale that up. The Milky Way galaxy contains an estimated 200 to 400 billion stars. That number is so large the human brain has no honest reference for it. If you counted one star per second without pause, without sleep, without stopping for a single moment, it would take you between 6,300 and 12,700 years to count every star in our galaxy alone. The observable universe contains an estimated 2 trillion galaxies. The Milky Way is one of them. And every single one of those galaxies, every spiral, every elliptical, every irregular dwarf galaxy containing only a few 100 million stars, exists because gravity pulled hydrogen and helium together in the aftermath of the Big Bang and never let go. Gravity does not create matter. It organizes it. That distinction is everything. In the earliest moments after the Big Bang, the universe was an extraordinarily hot, dense, nearly uniform plasma of particles and radiation. Nearly uniform, but not perfectly so. There were tiny fluctuations in density, regions where matter was fractionally more concentrated than the surrounding environment. These fluctuations were quantum in origin, embedded in the structure of space-time itself from the very first moments of cosmic inflation. And gravity, responding to every concentration of mass, no matter how small, began to amplify those fluctuations. The denser regions pulled surrounding matter inward. As they grew denser, their gravitational pull increased. As their pull increased, they pulled in more matter. This process, called gravitational collapse, is the mechanism behind every structure in the universe above the scale of individual atoms. It took approximately 379,000 years after the Big Bang for the universe to cool enough for neutral hydrogen atoms to form for the first time, an era called recombination. Before that point, the universe was so hot and ionized that photons could not travel freely, They were constantly scattered by free electrons. The moment neutral atoms formed, photons streamed freely outward. That light is still traveling through the universe today, cooled by cosmic expansion to a temperature of approximately 2.7 Kelvin, and we detect it as the cosmic microwave background radiation, a snapshot of the infant universe printed in microwaves across the entire sky. The tiny temperature variations in that ancient light, measured with extraordinary precision by satellites like COBE, WMAP, and most recently the Planck spacecraft, are the direct imprint of those primordial density fluctuations. They are the seeds. Everything that followed, every galaxy, every star, every planet, every moon, grew from those seeds under the patient influence of gravity. This is not a metaphor. It is observational fact. What makes gravity so uniquely powerful on cosmic scales, despite its extraordinary weakness at the particle level, is that it is universally attractive and has infinite range. Electromagnetism, which is dramatically stronger at short distances, exists in two forms: positive and negative charges, which tend to cancel each other out at large scales. A star, for instance, contains roughly equal numbers of protons and electrons. Its net electromagnetic charge is essentially zero. Its gravitational influence, on the other hand, does not cancel. Every kilogram of mass adds to the gravitational field. You cannot shield gravity. You cannot neutralize it. Every atom in the sun contributes to the gravitational field that holds the solar system together, and those contributions simply add up without limit. The weak nuclear force and the strong nuclear force, meanwhile, operate only at subatomic scales, on the order of 1 femtometer, which is 1/quadrillionth of a meter. They shape atomic nuclei, drive nuclear fusion in stellar cores, and govern radioactive decay. But they are invisible at the scale of centimeters, let alone the scale of light years. At the scale of the cosmos, only gravity and electromagnetism have any reach. And because electromagnetism cancels at large scales, the universe is, at its largest scales, a gravitational universe. Full stop. Which leads to a question that has challenged physicists for over a century. If gravity is so weak, if you can overcome Earth's gravitational pull on a paperclip with a small toy magnet, demonstrating with a trivial domestic experiment that electromagnetism can outmuscle Earth's entire gravitational field in a single motion, how does it build structures of such incomprehensible scale and mass? How does a force that struggles to hold a paperclip against a magnet manage to collapse clouds of gas containing more mass than 1,000,000 suns into a single stellar nursery? How does it compress matter so completely that a star 1.4 times the mass of the sun collapses into a sphere with a diameter of roughly 22 kilometers, generating a gravitational field so intense that a neutron on its surface would weigh approximately 90 sextillion times more than it does on Earth? The answer is time. Gravity's secret weapon is not strength, it is patience. Given enough time, and the universe is 13.8 billion years old, even the weakest force in nature becomes an architect of unimaginable power. A cloud of hydrogen gas in deep space, barely denser than the surrounding interstellar medium, has a gravitational field so faint it would take millions of years to produce a measurable effect. But millions of years is nothing to the universe. The cloud contracts. Its center grows denser. As it grows denser, the gravitational pull at its center increases. As the pull increases, collapse accelerates. Temperature and pressure rise. And if the cloud contains enough mass, a threshold known as the Jeans mass, calculated in 1902 by the British physicist Sir James Jeans, the collapse continues until the core reaches temperatures of approximately 10 million Kelvin. At that point, hydrogen nuclei begin fusing into helium. A star ignites. That process, from diffuse gas cloud to nuclear burning star, can take between 100,000 and several million years depending on the mass of the forming star. The sun itself took approximately 50 million years to reach what astronomers call the main sequence, the stable phase of hydrogen burning that defines an adult star. It has been burning ever since, for approximately 4.6 billion years, and will continue to do so for another 5 billion years before exhausting its core hydrogen supply. Every star you see in the night sky is the product of exactly this process, repeated across the universe 200 to 400 billion times in the Milky Way alone. And yet, here is where the story becomes genuinely strange. When astronomers mapped the distribution of visible matter in the universe and tried to calculate whether there was enough gravitational force from stars, gas, and dust to explain the structures they observed, something was wrong. The numbers did not add up. Galaxies were rotating too fast. Galaxy clusters were holding together with too much force. The cosmic web of large-scale structure was too pronounced to be explained by visible matter alone. Something else was there. Something massive. Something that emitted no light, reflected no radiation, and interacted with ordinary matter only through gravity. Dark matter. And it outweighs everything we can see by a ratio of approximately 5-1. For most of human history, the night sky was a ceiling. A fixed dome of light and darkness that repeated itself with such mechanical precision that ancient civilizations built entire calendars, agricultural systems, and religious frameworks around it. The Babylonians tracked the motion of planets across the sky with a sophistication that modern historians still find remarkable. Clay tablets dating back to the 7th century BCE contain mathematical sequences describing the velocity of Jupiter along the ecliptic that anticipate techniques not formally developed in European mathematics until the 14th century CE. The Mayans calculated the synodic period of Venus, the time it takes for Venus to return to the same position relative to the Sun as seen from Earth, to an accuracy within 2 hours over a 500-year cycle, without telescopes, without calculus. Using only naked eye observation and the accumulation of recorded data across generations. All of this was possible because gravity, while not yet understood as a force or a geometric property of space-time, was producing effects so consistent and so periodic that pattern recognition alone could describe them with extraordinary fidelity. The sky was a clock, and for thousands of years, humanity was content to read its face without understanding its mechanism. That changed in the 17th century when the mechanism became visible. Johannes Kepler, working in the early 1600s from the extraordinarily precise naked-eye observational data compiled by Tycho Brahe, data collected before the telescope existed, using custom-built instruments capable of measuring angular positions in the sky to within 1 arc-minute, discovered 3 empirical laws describing planetary motion. Planets orbit the sun in ellipses, not circles. A line connecting a planet to the sun sweeps equal areas in equal times, meaning planets move faster when closer to the sun and slower when farther away. And the square of a planet's orbital period is proportional to the cube of its average distance from the sun. These were not theories. They were patterns extracted from decades of observational data with painstaking mathematical discipline. Kepler had no explanation for why these patterns existed. He simply demonstrated with a precision that startled his contemporaries that they did. Isaac Newton provided the explanation. His law of universal gravitation, published in the Principia Mathematica in 1687, stated that every mass in the universe attracts every other mass with a force proportional to the product of their masses and inversely proportional to the square of the distance between them. With this single equation, Newton not only explained Kepler's 3 laws, but derived them mathematically from first principles. He demonstrated that the same force pulling an apple toward the ground, a force whose acceleration at Earth's surface is approximately 9.8 meters per second squared, is the identical force keeping the moon in orbit. He calculated the moon's orbital acceleration from the inverse square law using the known distance between the Earth and moon, approximately 384,000 kilometers, and found it matched observation to within the measurement precision available to him. The universe, Newton concluded, runs on a single gravitational law, operating identically from the surface of the Earth to the most distant observable body. For over 2 centuries, this framework was essentially perfect. Every planet moved as Newton's equations predicted. Every comet followed the calculated elliptical or hyperbolic trajectory. When the position of Uranus began showing small but persistent deviations from its predicted orbit in the early 19th century, astronomers did not conclude that Newton was wrong. They concluded there must be another planet, not yet discovered, perturbing Uranus gravitationally. Using only mathematics, applying Newton's law in reverse, calculating what mass at what position would produce the observed deviations, The French mathematician Urbain Le Verrier predicted the existence and location of Neptune in 1846. The German astronomer Johann Galle pointed his telescope at Le Verrier's predicted position on the night of September 23, 1846, and found Neptune within 1 degree of arc from the predicted location. It was one of the most spectacular confirmations of a physical theory in the history of science. Gravity, as Newton described it, was not merely a description, it was a precise predictive engine. Then came Mercury. Mercury's orbit precesses. The ellipse it traces around the Sun slowly rotates over time, so that the point of closest approach to the Sun, called the perihelion, shifts slightly with each orbit. This precession was known and largely explained by the gravitational tugs of other planets, particularly Venus and Jupiter. But when astronomers calculated the total precession expected from all known planetary perturbations and compared it to the observed value, there was a residual discrepancy of approximately 43 arcseconds per century. 43 arcseconds per century is an almost invisibly small number. It corresponds to a shift of less than 1/100th of a degree per century in the orientation of Mercury's orbit. And yet it was real, consistent, and stubbornly resistant to explanation within Newtonian gravity. Le Verrier himself, who had triumphantly predicted Neptune, spent years attempting to explain Mercury's anomalous precession by proposing the existence of yet another undiscovered planet orbiting between Mercury and the Sun, which he named Vulcan. Decades of searches found nothing. The resolution came in November 1915, when Albert Einstein submitted the final field equations of general relativity to the Prussian Academy of Sciences. General relativity replaced Newton's conception of gravity as a force acting at a distance with an entirely different framework. Gravity is the curvature of four-dimensional spacetime caused by the presence of mass and energy. Objects do not fall toward massive bodies because a force pulls them. They follow the straightest possible path, called a geodesic, through curved spacetime. Near a sufficiently massive body, those geodesics curve inward, producing what we experience as gravitational attraction. Einstein calculated the precession of Mercury's perihelion using the full machinery of general relativity, which predicts small but measurable corrections to Newtonian gravity in regions of strong gravitational fields or near the speed of light. The result was exactly 43 arcseconds per century. Not approximately. Exactly. Einstein later described this moment as one of the most powerful emotional experiences of his scientific life. The theory had not been adjusted to fit Mercury. It had produced the answer from pure mathematics. General relativity was confirmed spectacularly during the solar eclipse of May 29, 1919. During a total solar eclipse, stars near the Sun's limb become briefly visible. Einstein's theory predicted that the Sun's mass would curve spacetime enough to deflect the path of light from background stars passing near the Sun, causing them to appear shifted from their true positions by a measurable angle. The predicted deflection for a ray of light grazing the Sun's edge was approximately 1.75 arcseconds. Expeditions led by Arthur Eddington, one to the island of Principe off the west coast of Africa, and one to Sobral in Brazil, photographed the star field around the eclipsed Sun and compared the apparent positions of stars to their catalogued positions. The measured deflections matched Einstein's prediction. The following day, the Times of London carried the headline, "Revolution in Science, New Theory of the Universe." Newton had not been wrong. He had been incomplete. General relativity introduced a set of conceptual consequences that took decades to fully absorb. Space-time near a massive object is not merely curved, it runs at a different rate. Time passes more slowly in stronger gravitational fields. This is not a philosophical abstraction, it is a measured, engineering-relevant physical reality. The GPS satellites orbiting Earth at approximately 20,000 kilometers altitude experience weaker gravity than clocks on the surface and therefore run faster by approximately 45 microseconds per day due to gravitational time dilation, partially offset by a slowing effect from their orbital velocity. Without corrections accounting for both effects, GPS position calculations would accumulate errors of roughly 10 kilometers per day. Every time a navigation system guides a vehicle accurately through a city, it is implicitly confirming Einstein's general relativity dozens of times per second. At stellar scales, the consequences become more extreme. In regions of extreme space-time curvature, near neutron stars, near the event horizons of black holes, the predictions of general relativity diverge radically from Newtonian expectations. And it is precisely in those extreme environments that the deepest questions about gravity begin to surface. Because general relativity, for all its precision and elegance, is a classical theory. It describes a smooth, continuous space-time. Quantum mechanics, the framework governing the behavior of matter and energy at subatomic scales, describes a universe that is fundamentally discrete, probabilistic, and governed by uncertainty. The two theories are each extraordinarily accurate within their respective domains. They are also mathematically incompatible. Every attempt to construct a quantum theory of gravity, a framework that would describe gravity the way quantum electrodynamics describes electromagnetism, has encountered fundamental obstacles that remain unresolved after nearly a century of effort. String theory, loop quantum gravity, causal dynamical triangulation. Each approach has produced partial insights and significant mathematical structures. None has produced a complete, experimentally confirmed quantum theory of gravity. This is the open wound at the center of theoretical physics. And it matters not merely as an abstract intellectual puzzle. There exist physical situations in the universe, the interior of black holes, the first fraction of a second after the Big Bang, where both quantum effects and extreme gravity are simultaneously important. In those regimes, neither general relativity nor quantum mechanics alone is sufficient. A complete description of those environments requires a theory we do not yet have. The universe, it turns out, built its largest structures using a force whose deepest nature remains beyond our complete understanding. And the structures it built are stranger than anything Newton or Einstein initially anticipated. Because when astronomers in the 20th century began systematically mapping how galaxies actually move, not how they should move according to the distribution of visible matter, but how they demonstrably, observationally, measurably do move, the numbers refused to cooperate. Galaxies at the outer edges of spiral systems were orbiting their centers far too fast. In a system governed purely by the gravity of its visible stars and gas, orbital velocity should decrease with distance from the center, following a predictable curve derived directly from Newtonian and Einsteinian gravity. It does not. The rotation curves of spiral galaxies are flat. Stars at the outer edges orbit just as fast, sometimes faster, than stars much closer to the galactic center. The physics is unambiguous. Either the distribution of mass in galaxies is radically different from what we can observe, or our understanding of gravity itself breaks down at galactic scales. One of those possibilities leads to dark matter. The other leads somewhere far more unsettling. The first person to take the rotation problem seriously, not as a measurement error, not as an instrumental artifact, but as a genuine physical signal demanding a physical explanation, was a Swiss astronomer named Fritz Zwicky. In 1933, Zwicky was studying the Coma cluster, a massive collection of galaxies approximately 320 million light-years from Earth, containing over 1,000 individual galaxies bound together by gravity into a single gravitational system. To estimate the cluster's total mass, Zwicky used the virial theorem, a relationship from classical mechanics stating that for a gravitationally bound system in equilibrium, the total kinetic energy of its components is equal to half the magnitude of the total gravitational potential energy. He measured the velocities of individual galaxies within the cluster using the Doppler shift of their spectral lines, the same physical principle that makes an ambulance siren drop in pitch as it passes, and calculated how much total mass would be required to gravitationally bind a system whose members were moving at those speeds. The answer was approximately 400 times larger than the mass he could account for from the visible light of the galaxies themselves. Zwicky called it Dunkel Materie, dark matter. He was largely ignored for decades. The measurement was considered too uncertain, the conclusion too radical. The instrumentation of the 1930s was genuinely limited, and it was reasonable to attribute the discrepancy to systematic errors in distance measurements or in the mass-to-light ratios assumed for the galaxies. Science does not abandon successful frameworks on the basis of a single anomalous dataset. That is not a failure of imagination. That is the correct epistemological response to uncertain data. The anomaly refused to go away. In the 1960s and 70s, the American astronomer Vera Rubin, working with her colleague Kent Ford and his newly developed image tube spectrograph, an instrument sensitive enough to measure Doppler shifts in the spectral lines of stars at the outer edges of spiral galaxies, began systematically mapping the rotation curves of spiral galaxies in detail that had never before been possible. A rotation curve plots the orbital velocity of stars and gas as a function of their distance from the galactic center. In a system where most of the mass is concentrated at the center, as the distribution of visible stars strongly suggested, Newtonian gravity makes a clear prediction. Interior to the bulk of the mass, orbital velocity should rise with distance from the center, as more mass is enclosed within the orbit. Exterior to the bulk of the mass, orbital velocity should fall with distance, following what is called a Keplerian decline, the same pattern seen in the solar system, where Mercury orbits at approximately 47 kilometers per second and Neptune at approximately 5.4 kilometers per second. The outer planets are slow precisely because they sit far from where most of the solar system's mass is concentrated, in the Sun. Galaxy after galaxy, Rubin and Ford found something categorically different. The rotation curves did not decline at large radii, they were flat. Stars at the far outer edges of spiral galaxies were orbiting at essentially the same velocities as stars much closer to the center. In the Andromeda Galaxy, our nearest large spiral neighbor at approximately 2.5 million light-years distance, stars at the outermost measurable radii were orbiting at velocities essentially identical to those much deeper inside the disk. The same pattern appeared in NGC 300, in M33, in galaxy after galaxy across the sample. The flatness was not an occasional anomaly, it was universal. The physics of what a flat rotation curve implies is direct and unambiguous. If orbital velocity remains constant with increasing distance from the center, and if orbital velocity is determined by the gravitational pull of enclosed mass, then the enclosed mass must continue to increase linearly with radius, even as the visible stellar disk thins out and fades. In other words, there must be mass present in the outer regions of galaxies and extending well beyond the visible stellar disk, that is not accounted for by any observed component. The total mass implied by the flat rotation curves is typically 5 to 10 times larger than the mass of all the visible stars and gas combined. That invisible mass component is what we now call a dark matter halo, a roughly spherical distribution of non-luminous matter extending far beyond the visible disk of a galaxy, sometimes to radii 2 to 3 times larger than the optical disk itself. The Milky Way's visible disk spans approximately 100,000 light-years in diameter. Its dark matter halo is estimated to extend to a radius of between 300,000 and 600,000 light-years. The mass of the Milky Way's dark matter halo is estimated at approximately 1 trillion solar masses, compared to roughly 60 billion solar masses in visible stars. The halo outweighs the visible galaxy by a factor of roughly 15 to 1. The natural question is what dark matter actually is. And this is precisely where observational certainty gives way to one of the deepest unresolved problems in physics. What we know about dark matter from observation is substantial. It interacts gravitationally. It exerts gravitational pull on ordinary matter and on light, and it responds to gravity from other mass concentrations. It does not interact electromagnetically. It emits no light, absorbs no light, and reflects no light at any wavelength across the entire electromagnetic spectrum, from radio waves to gamma rays. It does not interact via the strong nuclear force. Whether it interacts via the weak nuclear force remains an open experimental question. It is not composed of ordinary baryonic matter, protons, neutrons, and electrons, in any form that would have escaped detection. Massive compact objects like brown dwarfs, black holes, and neutron stars, collectively called MACHOs, massive astrophysical compact halo objects, were once considered a plausible explanation. Gravitational microlensing surveys, which can detect compact massive objects by the brief brightening they produce when passing in front of a background star, have ruled out MACHOs as a dominant component of dark matter across a wide range of possible masses. The leading theoretical candidate for the dark matter particle is called a WIMP, a weakly interacting massive particle. WIMPs are hypothetical particles with masses in the range of 10 to a few thousand times the mass of a proton, interacting with ordinary matter only through gravity and possibly the weak nuclear force. They arise naturally in several extensions of the standard model of particle physics, most notably supersymmetry, which predicts a spectrum of partner particles for every known particle in the standard model. The lightest supersymmetric particle, called the neutralino in many models, would be stable, electrically neutral, and massive enough to account for the observed dark matter density. This theoretical motivation made WIMPs the dominant focus of dark matter searches for roughly 3 decades. The experimental effort to detect WIMPs directly has been extraordinary in scale and sensitivity. Underground detectors, located deep beneath mountain ranges and in former mines to shield them from cosmic ray backgrounds, have been constructed with increasingly refined detection technologies. The Xenon experiment, operating at the Gran Sasso National Laboratory beneath approximately 1,400 meters of rock in the Italian Apennines, uses liquid xenon as a target material. A WIMP passing through the detector and colliding with a xenon nucleus would produce a tiny flash of scintillation light and a small ionization signal, recorded by arrays of sensitive photodetectors. The LEX Zeppelin detector, located approximately 1,500 meters underground in the Sanford Underground Research Facility in the former Homestake Mine in South Dakota, uses 10 tons of liquid xenon and represents the current frontier of WIMP sensitivity. As of the most recent published results, no confirmed WIMP signal has been detected. The experiments have not failed. They have succeeded in placing extraordinarily tight constraints on the interaction cross-section of WIMPs with ordinary matter, ruling out large regions of the theoretical parameter space that supersymmetric models had predicted. The null result is itself a profound scientific finding, eliminating entire classes of theoretical models. An alternative candidate is the axion, a hypothetical extremely light particle originally proposed in 1977 by physicists Roberto Peccei and Helen Quinn as a solution to an unrelated problem in quantum chromodynamics called the strong CP problem. Axions, if they exist, would be extraordinarily light, with masses perhaps 1 trillion times smaller than the electron mass, and would be produced in enormous quantities in the early universe. They interact with ordinary matter with such extreme feebleness that they would be essentially invisible by all conventional detection methods. Dedicated experiments like ADMX, the Axion Dark Matter Experiment at the University of Washington, search for axions by exploiting their predicted interaction with magnetic fields. In the presence of a strong magnetic field, axions would occasionally convert into photons at a rate that depends on the axion mass and coupling constant. ADMX uses a high-powered superconducting magnet and a microwave cavity tuned to resonate at the frequency corresponding to the expected axion-to-photon conversion. The search is ongoing, progressively scanning through the allowed axion mass range. No confirmed detection has been made. A third possibility, considerably more radical and considerably less widely accepted, is that dark matter does not exist at all, and that the discrepancy between observed galaxy dynamics and theoretical predictions reflects a genuine breakdown of Newtonian and Einsteinian gravity at low accelerations. This framework, called Modified Newtonian Dynamics, or MOND, was proposed by Israeli physicist Mordechai Milgram in 1983. MOND postulates that below a critical acceleration threshold of approximately 1.2 times 10 to the negative 10 meters per second squared, a value far smaller than any acceleration measurable in a terrestrial laboratory, the effective gravitational force deviates from the standard inverse square law. In regimes above this threshold, standard Newtonian gravity applies without modification. Below it, gravity falls off more slowly with distance, producing the flat rotation curves observed in galaxy outskirts without requiring any unseen mass. MOND reproduces the observed rotation curves of spiral galaxies with remarkable accuracy. Its predictive power in that specific domain is genuinely impressive. For a given galaxy's distribution of visible mass, MOND makes a unique prediction for the rotation curve with no free parameters beyond the universal critical acceleration constant. The predictions match observations across a wide range of galaxy types and masses. This success is not trivial, and it cannot be dismissed. The problem is that MOND fails at larger scales. Galaxy clusters, including the Coma cluster that Zwicky studied in 1933, require dark matter even within a MOND framework, The visible mass plus Mond corrections are still insufficient to explain the observed cluster dynamics. More compellingly, the bullet cluster, a system of two galaxy clusters that passed through each other approximately 150 million years ago at a relative velocity of approximately 3,000 kilometers per second, provides what many cosmologists consider the most direct observational evidence for dark matter. During the collision, the hot gas component of each cluster, which constitutes most of the visible baryonic mass, was slowed by electromagnetic interactions and ram pressure, lagging behind the galaxies. The dark matter halos, interacting only gravitationally and therefore effectively collisionless, passed through each other without slowing. Gravitational lensing maps of the bullet cluster show two distinct mass concentrations separated from the hot gas. Mass that is present where there is no visible matter, coinciding precisely with where collisionless dark matter halos would be expected after the collision. The geometry of the bullet cluster does not prove dark matter exists. It demonstrates that the dominant mass component of those clusters is spatially separated from the dominant baryonic component, a configuration that is natural within a dark matter framework and deeply problematic for any purely modified gravity theory that ties gravitational effects directly to the distribution of visible mass. The universe's largest structures are shaped by something we have never directly detected, never captured in a laboratory, and cannot yet identify from first principles. Its presence is written everywhere in the architecture of the cosmos. Its nature remains, as of today, unknown. And dark matter is only half the problem. In 1998, two independent teams of astronomers set out to measure the rate at which the expansion of the universe was slowing down. That framing, slowing down, was not an assumption born of carelessness. It was the only physically reasonable expectation given everything science understood about gravity at cosmological scales. The universe had been expanding since the Big Bang. Gravity, acting on every particle of matter across every megaparsec of space, should have been decelerating that expansion continuously since the beginning. The only question the two teams were trying to answer was how much deceleration, enough to eventually halt the expansion and reverse it into a big crunch, or just enough to let the universe coast toward a cold, diffuse, but still decelerating future. Neither team was prepared for what the data actually said. The two collaborations, the Supernova Cosmology Project, led by Saul Perlmutter at Lawrence Berkeley National Laboratory, and the High-Z Supernova Search Team, led by Brian Schmidt and Adam Rees, were using a specific class of stellar explosions called Type Ia supernovae as what astronomers call standard candles. A standard candle is any object whose intrinsic luminosity, the total amount of light it actually produces, is known independently of its distance. If you know how bright something truly is, and you measure how bright it appears from Earth, the difference between those two values tells you exactly how far away it is, using the inverse square law of light propagation. Apparent brightness falls off with the square of the distance. Type Ia supernovae arise in binary star systems where a white dwarf, the dense Earth-sized remnant of a star that has exhausted its nuclear fuel, accretes matter from a companion star. When the white dwarf's mass reaches approximately 1.4 solar masses, a threshold known as the Chandrasekhar limit, after the Indian-American astrophysicist Subramanian Chandrasekhar, who calculated it in 1930, the white dwarf can no longer support itself against gravitational collapse through electron degeneracy pressure. Carbon fusion ignites throughout the entire stellar interior almost simultaneously, releasing energy equivalent to roughly 1 to 2 times 10 to the 44 joules. Approximately the total energy output of the Sun over its entire 10 billion year main sequence lifetime, released in a matter of seconds. The explosion is visible across billions of light years, and because the trigger mechanism always occurs at the same mass threshold, the peak luminosity of Type Ia supernovae is remarkably consistent, making them among the most reliable distance indicators available to observational cosmology. Both teams were observing Type Ia supernovae in galaxies at cosmological distances, redshifts of approximately 0.3 to nearly 1, corresponding to light travel times of several billion years. By comparing the observed brightness of these distant supernovae to their expected brightness based on their measured redshifts, which indicate how fast the galaxy is receding and therefore serve as a proxy for distance in an expanding universe, the teams could measure whether the expansion had been faster or slower in the past than models predicted. In a decelerating universe, the expansion was faster in the past. Distant supernovae, seen as they were billions of years ago, should appear slightly brighter than a non-decelerating model would predict, because the universe was expanding faster when that light was emitted. The distant supernovae appeared dimmer than expected, not brighter. Dimmer meant farther away than the deceleration model predicted. Farther away meant the universe had not been expanding faster in the past. It had been expanding more slowly and had since sped up. The expansion of the universe is not decelerating, it is accelerating. Something is pushing the fabric of space-time outward at an increasing rate, overpowering gravity on the largest scales, driving galaxies apart faster and faster as time progresses. Perlmutter, Schmidt, and Rees were awarded the Nobel Prize in Physics in 2011 for this discovery. The citation described it, with characteristic scientific restraint, as a finding that had forever changed our view of the universe. The unknown component driving the acceleration was given a name: dark energy. The name is, in a precise sense, an admission of ignorance. It describes something whose effect is measured with high precision and whose nature is almost entirely unknown. What dark energy actually is, whether it is a fixed property of space itself, a dynamic field evolving over time, or a signal that general relativity requires modification at cosmological scales, remains one of the most actively contested questions in all of physics. The simplest mathematical description of dark energy is the cosmological constant, denoted by the Greek letter lambda, which Einstein himself introduced into his field equations in 1917, and then removed, famously calling it his greatest blunder after Edwin Hubble's observational confirmation of cosmic expansion in 1929 made a static universe unnecessary. In Einstein's original formulation, lambda represented a repulsive term added to counterbalance gravity and produce a static, non-expanding universe. In its modern cosmological interpretation, lambda represents the energy density of empty space itself, the vacuum energy. Empty space, in this framework, is not truly empty. It has an intrinsic energy content that does not dilute as the universe expands, unlike the energy density of matter and radiation, which decrease as the volume of the universe increases. As the universe expands, the total amount of vacuum energy grows proportionally with volume. The repulsive effect therefore grows over time relative to the attractive effect of matter, whose density is simultaneously decreasing. This is why the acceleration is a relatively recent phenomenon in cosmic history. For the first roughly 7 to 8 billion years after the Big Bang, matter density was high enough that gravity dominated. As the universe expanded and matter thinned out, vacuum energy came to dominate. The transition from deceleration to acceleration occurred approximately 5 to 6 billion years ago. The problem is that quantum field theory, the most successful theoretical framework in the history of physics, whose predictions of quantities like the anomalous magnetic moment of the electron match experimental measurements to better than 1 part in 1 trillion, predicts a value for the vacuum energy that is between 55 and 120 orders of magnitude larger than the value inferred from cosmological observations, depending on the assumptions used in the calculation. 120 orders of magnitude is 10 followed by 120 zeros times too large. This discrepancy, known as the cosmological constant problem, has been described by physicists as the worst prediction in the history of science. The quantum mechanical vacuum should be seething with energy at a density that would have caused the universe to expand so violently in its earliest moments that no structure, no atoms, no stars, no galaxies could ever have formed. Something cancels almost all of that vacuum energy down to the extraordinarily small residual value we observe. What performs that cancellation and why it is so extraordinarily precise without being exactly zero is not understood. An alternative to a fixed cosmological constant is a dynamic dark energy, a scalar field permeating all of space whose energy density evolves over time. The simplest class of such models is called quintessence, a term invoking the classical philosophical concept of a fifth fundamental element. In quintessence models, dark energy behaves like a fluid with a time-varying equation of state. The ratio of its pressure to its energy density changes as the universe evolves. If the equation of state parameter, denoted W, equals exactly -1, dark energy behaves identically to a cosmological constant. If W deviates from -1, Whether greater or less, it indicates a dynamic field rather than a fixed vacuum energy. Current observational constraints from the combination of Type Ia supernova data, the cosmic microwave background, and the large-scale distribution of galaxies place W remarkably close to -1. But the uncertainties are still large enough that a dynamic dark energy cannot be ruled out. In March 2024, the Dark Energy Spectroscopic Instrument, DESI, released its first year of results from a survey mapping the three-dimensional positions of approximately 6 million galaxies and quasars across the observable universe. DESI measures what are called baryon acoustic oscillations, a fixed characteristic scale imprinted in the distribution of galaxies by sound waves that propagated through the early universe plasma before recombination. These oscillations left a preferred clustering scale of approximately 490 million light-years, which can be measured across cosmic time and used as a standard ruler to trace the expansion history of the universe with high precision. The first DESI results, while not yet conclusive, showed mild statistical tension with a cosmological constant model, with the data showing a slight preference for a dark energy equation of state that has evolved over time. The statistical significance, approximately 2 to 3 sigma, falls below the conventional 5 sigma threshold required to claim a discovery. But the direction of the deviation has drawn intense attention from the cosmological community, as it is consistent with certain dynamic dark energy models. If dark energy is not a cosmological constant, if it is a field that evolves, that could strengthen or weaken, that could have been different in the past and will be different in the future, the long-term fate of the universe becomes radically less certain. A dark energy that grows stronger over time leads to a scenario called the Big Rip, in which the accelerating expansion eventually overcomes not just the gravity-binding galaxy clusters and individual galaxies, but ultimately the gravity and electromagnetic forces binding star systems, then planets, then molecules, then atoms themselves, shredding all structure in the universe in a finite time. Current observational constraints do not favor this scenario, but they cannot yet exclude it. What the acceleration of cosmic expansion established, definitively and irreversibly, is that the universe contains a component, comprising approximately 68% of its total energy content, that behaves in a manner fundamentally unlike anything in the standard model of particle physics, unlike any known form of matter or radiation, and unlike any prediction of unmodified general relativity without a cosmological constant. Combined with dark matter, which constitutes approximately 27% of the total energy content, ordinary baryonic matter, every atom in every star, planet, gas cloud, and human body in the observable universe accounts for only approximately 5% of what the cosmos actually contains. Gravity shaped everything we can see. But what we can see is a small fraction of what is there. The universe that human civilization has spent millennia observing, cataloging, and theorizing about, every star ever named, every galaxy ever photographed, every particle ever detected in a laboratory, is the surface layer of a reality whose dominant components remain fundamentally beyond our current understanding. The 5% that emits light, that interacts with our instruments, that constitutes every physical object ever touched or measured by human hands, is the exception. The remainder of the universe operates by rules we are only beginning to formulate. And somewhere within that remainder, within the dark matter that built the scaffolding of cosmic structure and the dark energy that is now dismantling the conditions for future structure formation, lies the answer to whether the universe we inhabit is one of stable permanence or of accelerating dissolution. The evidence, accumulating with each new survey and each new generation of detectors, points in one direction. Nothing in this universe lasts forever. Not galaxies, not stars, not the conditions that make structure possible. Gravity built everything. And something else, something we have named but not explained, is slowly, inexorably taking it apart. On the night of February 23, 1987, light from an explosion that had occurred 168,000 years earlier finally reached Earth. The source was a massive star designated Sandalik -69 degrees 202, a blue supergiant located in the Large Magellanic Cloud, a satellite galaxy of the Milky Way visible from the southern hemisphere. The star had a mass of approximately 20 times the mass of the Sun. It had spent roughly 11 million years fusing progressively heavier elements in its core, from hydrogen to helium, helium to carbon, carbon to neon, neon to oxygen, oxygen to silicon, and finally, silicon to iron. Iron is the endpoint. It is the most tightly bound atomic nucleus, the element from which no further fusion can extract net energy. When the iron core of a massive star reaches approximately 1.4 to 3 solar masses, electron degeneracy pressure can no longer halt gravitational collapse. The core collapses in less than 1 second. The outer layers, still falling inward, rebound off the suddenly incompressible core material in a shockwave that tears the star apart. Supernova 1987A, as it was designated, became the brightest supernova observable from Earth since the one recorded by the Danish astronomer Tycho Brahe in 1572. At its peak, it radiated energy equivalent to approximately 100 million suns. But the visible light explosion, spectacular as it was not the most significant signal the event produced. 3 hours before the optical brightening was detected, before any astronomer had seen anything unusual, neutrino detectors buried deep underground on opposite sides of the planet registered a brief but unmistakable burst of particles. The Kamiokande 2 detector in Japan detected 11 neutrinos. The Irvine, Michigan Brookhaven detector in the United States registered 8. The Baksan Neutrino Observatory in the Soviet Union detected 5. 24 neutrino events in total, arriving within a 12-second window from a source 168,000 light-years away. The core collapse of a massive star releases approximately 3 times 10 to the 46 joules of gravitational energy, roughly 100 times the total energy output of the Sun over its entire 10 billion-year life, 99% of which is radiated away as neutrinos in the first 10 seconds. Those neutrinos, traveling at speeds indistinguishably close to the speed of light, escaped the stellar interior essentially instantaneously while the optical explosion was still building. They crossed 168,000 light-years of intergalactic space and arrived at Earth, detectable, countable, and timed. The arrival of those 24 neutrinos confirmed in a single observational event the theoretical framework for core collapse supernovae that had been developed over decades. It confirmed that neutron stars form in stellar core collapse. It placed the tightest constraints then available on the neutrino mass. The fact that neutrinos of different energies arrived within seconds of each other over a baseline of 168,000 light-years placed an upper limit on the electron-neutrino mass of approximately 16 electron volts, since a massive particle traveling at below the speed of light would show energy-dependent arrival time differences that were not observed. And it demonstrated that neutrino astronomy, the detection of the universe through its most weakly interacting messengers, was not merely theoretical, it was operational. Supernova 1987A was also the first supernova close enough for the expanding remnant to be directly imaged over time by telescopes. The Hubble Space Telescope, launched in 1990, has tracked the development of the 1987A remnant across decades. The expanding ejecta, moving outward at approximately 7,000 kilometers per second, collided with a pre-existing ring of material expelled by the star during an earlier evolutionary phase, producing a glowing necklace of bright knots as the shockwave heated the ring material to millions of degrees Kelvin. As of the most recent observations, astronomers have been searching within the remnant for direct evidence of the neutron star the core collapse should have produced. The dense ejecta have made direct detection difficult, but infrared observations from the James Webb Space Telescope have revealed emission consistent with a central compact object, potentially the first direct detection of the neutron star produced by 1987A's core collapse, forming a data point that closes a loop opened by those 24 neutrinos 37 years earlier. Core collapse supernovae like 1987A are the primary mechanism by which the universe distributes heavy elements. The nuclear burning in massive stellar cores and the explosive nucleosynthesis of the supernova itself produces essentially all elements heavier than iron in nature, from cobalt and nickel through gold, platinum, and uranium. Every atom of gold on Earth was forged either in the core collapse of a massive star or, as more recent evidence suggests, in the collision of two neutron stars. The merger of neutron stars, called a kilonova, was directly observed for the first time on August 17, 2017, when the LIGO and Virgo gravitational wave detectors registered a signal designated GW170817, produced by two neutron stars spiraling into each other at a distance of approximately 130 million light-years in the galaxy NGC 4993. Within 2 seconds of the gravitational wave signal, the Fermi Gamma Ray Space Telescope detected a short gamma ray burst from the same sky location, the first direct confirmation of the long-theorized connection between neutron star mergers and short gamma ray bursts. Electromagnetic follow-up observations across dozens of telescopes worldwide detected the kilonova optical transient, whose spectral signatures confirm the production of heavy R process elements, including strontium and, by inference, significant quantities of gold and platinum. The estimated mass of gold produced in GW170817 alone was approximately 10 Earth masses. Gravity, in this context, is not only the architect of structure, it is the engine of chemistry. Without gravitational collapse igniting stellar cores, without the crushing pressures of core collapse producing neutron stars, without the orbital decay of neutron star binaries driven by gravitational wave emission over billions of years, the periodic table beyond iron would not exist. The calcium in bone, the iron in blood, the iodine in tissue. These were forged in stellar explosions driven by gravity. The gold in any ring on any human hand was produced in the collision of two dead stars, each one a remnant of gravity's most extreme compression of ordinary matter. The gravitational wave detection of GW170817 inaugurated what astronomers call multi-messenger astronomy, the simultaneous observation of a single cosmic event through multiple distinct physical carriers of information: gravitational waves, gamma rays, X-rays, ultraviolet light, optical light, infrared light, and radio waves. Each messenger carries different information about different physical processes occurring at different timescales within the same event. Gravitational waves encode the orbital dynamics and masses of the merging compact objects with extraordinary precision. Gamma rays trace the relativistic jet launched by the merger. Optical and infrared emission traces the kilonova nucleosynthesis. Radio emission tracks the long-term evolution of the jet as it decelerates into the surrounding interstellar medium. No single observatory, no single wavelength, no single physical messenger gives the complete picture. GW170817 was the first event where all messengers were captured together. The instrument that made gravitational wave detection possible, LIGO, the Laser Interferometer. Gravitational Wave Observatory represents one of the most technically demanding scientific instruments ever constructed. Each LIGO facility consists of two perpendicular arms 4 kilometers in length. A laser beam is split and sent down each arm simultaneously, reflected off mirrors suspended by multi-stage pendulum systems designed to isolate them from any mechanical vibration, and recombined at a central detector. When a gravitational wave passes through the instrument, it stretches space-time along one arm and compresses it along the other, producing a minuscule difference in the length of the two arms that the recombined laser beams register as a change in interference pattern. The sensitivity required is staggering. LIGO detects length changes of approximately 1,000th the diameter of a proton, a displacement of roughly 10 to the negative 18 meters, across a 4-kilometer baseline. Expressed differently, if one LIGO arm were stretched to the distance between Earth and the nearest star, Proxima Centauri, at approximately 4.2 light-years, the signal being detected would correspond to a length change of approximately 40 micrometers, less than the width of a human hair. The first confirmed gravitational wave detection, GW170914, was registered on September 14, 2015, and announced publicly on February 11, 2016. The signal lasted approximately 0.2 of a second and was produced by the merger of two black holes with masses of approximately 36 and 29 solar masses, respectively, at a distance of approximately 1.3 billion light-years. In the final moments before merger, the two black holes were orbiting each other approximately 150 times per second, radiating gravitational energy at a peak power of approximately 3.6 times 10 to the 49 watts, more power than the combined luminosity of all stars in the observable universe during that fraction of a second. The total mass lost to gravitational wave radiation during the merger was approximately 3 solar masses, 3 times the mass of the Sun converted entirely to ripples in the fabric of spacetime, propagating outward at the speed of light. The detection of GW 15914 confirmed a prediction of general relativity that Einstein himself had doubted could ever be observationally verified. It confirmed the existence of stellar mass black holes with masses significantly larger than theoretical models had predicted. It opened an entirely new observational window on the universe, one that is completely opaque to electromagnetic radiation, capable of probing regions and events that emit no light whatsoever. The merger of black holes radiates no photons. It is invisible to every telescope ever built that detects electromagnetic radiation. It is visible only as a distortion in spacetime itself, propagating across billions of light years, compressing and stretching the 4-kilometer arms of a terrestrial detector by less than 1,000th the diameter of a proton. As of the most recent LIGO-Virgo-Cagra observing runs, over 90 confirmed compact binary merger events have been detected and cataloged, including black hole mergers, neutron-star mergers, and candidate black hole neutron-star merger events. Each detection adds a data point to the growing census of compact objects in the universe, objects that exist only because gravity pursued matter to its absolute compressional limit, past the point where any known force could provide resistance. At the center of the Milky Way, at a distance of approximately 26,000 light-years from Earth, sits an object that represents gravity's most extreme stable configuration, a supermassive black hole designated Sagittarius A, with a mass of approximately 4 million solar masses contained within a region smaller than the orbit of Mercury around the Sun. Its existence was inferred for decades from the orbital motions of stars in its immediate vicinity, stars moving at thousands of kilometers per second in tight elliptical orbits whose focal point coincides with no visible object whatsoever. The star designated S2, monitored continuously since the 1990s, completes one full orbit around Sagittarius A in approximately 16 years, reaching a closest approach of approximately 120 astronomical units from the black hole at a velocity of approximately 7,600 kilometers per second, approximately 2.5% of the speed of light. The orbital data place the mass of the central object at 4.15 million solar masses with a precision of better than 1%. Nothing but a black hole can contain that mass within the observed orbital radius. On April 10, 2019, the Event Horizon Telescope collaboration released the first direct image of a black hole's shadow, the supermassive black hole at the center of the galaxy M87, located approximately 55 million light-years from Earth, with a mass of approximately 6.5 billion solar masses. The image, reconstructed from simultaneous radio observations by 8 telescopes distributed across the globe from Hawaii to the South Pole, showed a bright asymmetric ring of emission surrounding a central dark region, the photon ring, and the shadow cast by the black hole's event horizon against the background of the glowing accretion disk. The asymmetry in the ring brightness is caused by relativistic beaming. The side of the disk rotating toward the observer appears brighter due to the Doppler effect. The size and shape of the shadow match the predictions of general relativity for a black hole of that mass to within the measurement uncertainties. In 2022, the Event Horizon Telescope released the first image of Sagittarius A itself, the black hole at the center of our own galaxy. The imaging was technically more challenging than M87 due to the rapid orbital motion of gas in the accretion flow around the lower mass object, which changes on timescales of minutes rather than days. The resulting image showed the same characteristic ring structure, consistent with general relativity's predictions at the center of the Milky Way. Gravity's most extreme products, neutron stars, black holes, the supermassive engines at the centers of galaxies, are no longer theoretical constructs. They have been weighed, imaged, and heard. Their mergers have been detected as ripples in space-time crossing billions of light-years. Their shadows have been photographed with a telescope the size of the Earth. The force that built the universe has also revealed the sharpest boundary in physics, the event horizon, beyond which no information, no light, no signal of any kind can escape. What happens inside remains, by the fundamental structure of general relativity, permanently beyond the reach of any external observer. That boundary is not a failure of instrumentation. It is written into the geometry of space-time itself. There is a timescale that dwarfs everything discussed in this documentary by so many orders of magnitude that the entire history of the universe to this point, 13.8 billion years of expansion, structure formation, stellar evolution, and cosmic chemistry, becomes a rounding error. It is called the Stelliferous Era, and it refers to the period in cosmic history during which stars exist. That era began approximately 100 million years after the Big Bang, when the first generation of massive stars ignited in the densest regions of the primordial gas distribution. It will end, according to current stellar evolution models, in approximately 100 trillion years, 10,000 times the current age of the universe, when the last red dwarf stars, the smallest and most fuel-efficient stellar objects, finally exhaust their hydrogen supply and fade into cold, dark stellar remnants. 100 trillion years. If the current age of the universe were compressed into a single calendar year, with the Big Bang occurring at midnight on January 1st, the formation of the solar system would occur in early September. The entirety of recorded human history would occupy the final fraction of a second before midnight on December 31st, and the end of the Stelliferous Era would occur approximately 7,200 years from now on that compressed calendar. The universe is not old. By the measure of its own future, it is extraordinarily young. We exist, as a civilization and as a species, in what is cosmologically speaking, the early morning of the universe's life. What follows the Stelliferous Era is a sequence of epochs whose timescales are so extreme that they require a different relationship with numbers than ordinary scientific reasoning demands. The degenerate era follows, lasting from approximately 100 trillion to approximately 10 to the 40th years after the Big Bang. During this period, the primary inhabitants of the universe are white dwarfs, neutron stars, and black holes, the gravitational remnants of the Stelliferous Era. White dwarfs cool slowly over immense timescales, radiating their residual thermal energy into an increasingly dark and cold universe. The universe during the degenerate era is not empty. It is structured in the sense that gravitational bound systems, galaxies, clusters, still exist, even as their stellar populations have been replaced by dark remnants. But it is profoundly dark and cold, lit only by the faint glow of cooling white dwarfs and the occasional collision or accretion event that briefly rekindles nuclear burning. Proton decay, if it occurs on the timescales predicted by certain grand unified theories, with a half-life of approximately 10 to the 34 years, would dissolve all baryonic matter during this epoch, reducing white dwarfs and neutron stars to dispersed leptons and radiation. As of the current experimental constraints from large underground detectors, including Super Kamiokande in Japan, proton decay has not been observed, placing the proton lifetime at greater than approximately 10 to the 34 years for certain decay channels. Whether protons ultimately decay is unknown. If they do not, white dwarfs and neutron stars persist until quantum tunneling processes, operating on timescales of approximately 10 to the 76th years, cause their constituent matter to rearrange into iron nuclei, the most stable nuclear configuration, and eventually tunnel into black holes. Black holes themselves are not permanent. In 1974, the British physicist Stephen Hawking derived, using a combination of general relativity and quantum field theory, that black holes must emit thermal radiation, now called Hawking radiation, as a consequence of quantum effects near the event horizon. The temperature of this radiation is inversely proportional to the black hole's mass. The more massive the black hole, the colder and more feeble its Hawking radiation, and the slower its evaporation. A stellar mass black hole of 10 solar masses has a Hawking temperature of approximately 6 billionths of a Kelvin, so cold that it absorbs vastly more energy from the cosmic microwave background radiation, currently at 2.7 Kelvin, than it emits. Such a black hole will not begin to lose mass to Hawking radiation until the universe has expanded and cooled sufficiently, that the cosmic microwave background temperature drops below its Hawking temperature, a process requiring an immense but finite time. The evaporation timescale for a black hole scales with the cube of its mass. A stellar mass black hole of 10 solar masses would require approximately 2 times 10 to the 74th years to fully evaporate. The supermassive black hole at the center of M87, with a mass of 6.5 billion solar masses, would require approximately 10 to the 100 years to evaporate. In the final stages of evaporation, as the black hole loses mass, its Hawking temperature rises, its luminosity increases, and the process accelerates into a terminal burst of high-energy gamma radiation. What precisely happens in the final Planck-scale moments of black hole evaporation, whether the information content of everything that ever fell into the black hole is preserved in some form in the outgoing Hawking radiation, or whether it is permanently destroyed, is the black hole information paradox, one of the deepest unresolved questions in theoretical physics. Its resolution requires a complete theory of quantum gravity that does not yet exist. After the last black holes have evaporated, after 10 to the 100 years or more, the universe enters what physicists call the dark era. There is no baryonic matter. There are no stars, no planets, no compact remnants of any kind. The universe consists of an expanding, cooling sea of photons, neutrinos, electrons, positrons, and gravitational waves, the final dispersed products of Hawking evaporation and proton decay, growing ever more dilute as space continues to expand. If dark energy remains constant as a cosmological constant, the expansion continues indefinitely and accelerates. The density of radiation falls towards zero. Temperatures approach absolute zero asymptotically. The universe does not end in a dramatic final event. It approaches a state of maximum entropy, thermodynamic equilibrium, in which no further work can be extracted from any physical process, no temperature gradients exist to drive any reaction, and nothing more happens. This is what physicists call the heat death of the universe. It is a profoundly strange destination for a cosmos that began in a state of almost incomprehensible energy density and complexity. 13.8 billion years ago, all the matter and energy now distributed across the observable universe, a sphere approximately 93 billion light-years in diameter, was compressed into a volume smaller than an atomic nucleus at a temperature exceeding 10 to the 32 Kelvin, governed by physical conditions that no terrestrial experiment can reproduce. From that initial state, gravity organized matter with such patience and precision that it produced hydrogen clouds, then stars, then planetary systems, then the chemical conditions for molecular complexity, and ultimately for biology, cognition, and the capacity to reconstruct the history of the cosmos from first principles. That reconstruction is itself a physical phenomenon. The human brain, a structure of approximately 86 billion neurons connected by roughly 100 trillion synaptic junctions, consuming approximately 20 watts of power, is assembled from atoms forged in stellar cores and supernova explosions, organized by evolutionary processes ultimately driven by the energy output of a 4.6 billion-year-old star on a rocky planet held in orbit by gravity at a distance of approximately 1 astronomical unit from that star. The fact that this arrangement of stellar ash can model the formation of galaxy clusters, derive the equations of general relativity, build instruments sensitive enough to detect a gravitational wave from a black hole merger 1.3 billion light-years away, and trace the history of the universe back to within fractions of a second of the Big Bang. That fact has no parallel in any known physical system. It is the most improbable arrangement of matter that gravity has produced that we are aware of. And it is temporary. Every star that currently exists will eventually exhaust its fuel. The Sun will leave the main sequence in approximately 5 billion years, expanding into a red giant that will likely engulf the inner planets including Earth, then shed its outer layers as a planetary nebula and collapse into a white dwarf of approximately 0.5 to 0.6 solar masses. The Milky Way and Andromeda galaxies are approaching each other at approximately 110 kilometers per second and will begin to merge in approximately 4.5 billion years, eventually producing a large elliptical galaxy that some astronomers have named Milkomeda. The merger will not destroy individual star systems. The distances between stars are too vast for direct collisions to be common, but it will dramatically reshape the galactic structure and alter the orbits of billions of stars over timescales of hundreds of millions of years. On scales of tens of billions of years, accelerating expansion will push all galaxies currently observable beyond the cosmological event horizon, the distance beyond which the recession velocity of space exceeds the speed of light, making any future communication or observation impossible. Galaxies currently visible at distances of tens of billions of light-years will simply disappear from the observable universe, their light unable to reach us against an accelerating cosmic expansion. Civilizations that might exist in the far future, if any survive on those timescales, will observe a universe that appears to contain only their own local galaxy or galaxy group. All evidence of the large-scale structure, the cosmic web, the billions of galaxies that 21st century astronomy has cataloged, all of it will have receded beyond observational reach. The universe will appear, from any vantage point, to be essentially empty. The evidence for the Big Bang, for cosmic expansion, for the existence of other galaxies, all of it will have been erased from the observable sky by the very process of accelerating expansion. This is not a distant abstraction. It is a physical consequence of a measured cosmological parameter, the value of the dark energy density, that we have been observing in supernova data since 1998. What does not disappear on any timescale is the physics. The laws governing gravity, quantum mechanics, thermodynamics, and the behavior of matter and energy appear to be fixed properties of this universe, not historical artifacts that could have been otherwise, but deep structural features of physical reality that have held without measurable variation from the earliest moments accessible to observation to the present day. The fine structure constant, which governs the strength of electromagnetic interactions, has been measured in the spectral lines of quasars at redshifts, corresponding to light travel times of over 10 billion years. Its value, to the precision achievable, is identical to its laboratory-measured value today. The gravitational constant, measured through the orbital dynamics of binary pulsars, pairs of neutron stars orbiting each other with a precision that makes atomic clocks look imprecise, shows no evidence of variation over cosmic time. The universe is governed by rules that are, as far as we can determine, universal and permanent. The objects change, the structures evolve and dissolve, the stars ignite and die. The black holes evaporate over timescales that dwarf the current age of the universe by factors of 10 to the 80 or more. But the equations that describe all of this, the field equations of general relativity, the Schrödinger equation, the standard model Lagrangian, persist as the unchanging grammar of physical reality. Gravity wrote the universe we inhabit. It pulled hydrogen into stars. It collapsed stars into the heavy elements that built planets and organisms. It curved space-time deeply enough to produce black holes whose event horizons mark the sharpest boundary in known physics. It will, over timescales that render the current age of the universe negligible, dismantle every structure it assembled, and through all of it, through the ignition of the first stars, through the construction of the cosmic web, through the slow cooling of white dwarfs in a darkening universe, through the final evaporation of the last black holes into thermal radiation, the laws that govern it will not change by a single measurable digit. We are made of the product of gravity's patience. We exist in the brief window when the universe is structured enough for complexity, warm enough for chemistry, and young enough for stars. The window is open. For now.